All right, guys, so we've been working through acids and bases. We've talked about strong acids and what makes a strong acid. We've talked about weak acid, what makes a weak acid, strong base, weak base, and so on and so forth. We've talked about Ka and how to calculate Kb and Ka using Kw. Keep in mind Ka and Kb, those equilibrium expressions, all that basically is Ka is your equilibrium constant for anything acting like an acid, which means it's giving up a hydrogen at that point in time. Kb is anything acting like a base, meaning it's accepting a hydrogen in that particular solution. And these can go back and forth between each other using Kw and using that equation. We've talked about how to calculate pH based off the hydronium or hydroxide concentration, POH in that case. Now let's look at actually solving pH for when we have a weak acid solution. So we know if it's a strong acid solution, we can just use the concentration of the acid itself because a strong acid is going to dissociate completely. But what if it doesn't dissociate completely? Then we have to use equilibrium to determine how much hydronium actually is going to be produced. So let's kind of work through this one together. What is the pH of a 1.2 molar solution of HF given a Ka of 7.2 times 10 to the negative 4? So keep in mind, you really should know the 8 strong acids, but here's the deal. If they're giving you, or I'm giving you a Ka, it's a weak acid. So while it's very, very beneficial to be able to identify those strong acids and bases very, very readily, it's also important to recognize that a strong acid and a strong base does not have a Ka or a Kb. So if you're given a Ka or Kb, you're dealing with something that's considered weak, whether it's a weak acid or weak base. So with that being said, the first thing we need to do here is write our equilibrium expression. Okay, and this is the solution. All acids are aqueous. We're going to put water in our equilibrium equation. And this is going to act like an acid. So according to the Bronsted-Lowry model or the Arrhenius model, what does an acid do? It gives up a hydrogen. So we end up with hydronium and fluorine ions. Okay, so not too bad. We can handle that pretty readily. Now, how do we solve an equilibrium expression? And what are we solving for? We're trying to find pH. Remember, pH is calculated off of the hydrogen or hydronium, H3O plus, concentration. So what are we actually looking for? We're looking for this species concentration at equilibrium. Well, how do we do that? We use an ice table. So, again, nothing new that we haven't already done before. So remember, I is initial, so in this case, 1.20 molar. We don't care about water, so this is kind of new where we really haven't had a lot of solids and liquids that we've played with thus far. So I'm just going to put an X underneath water. We start out with 0 of this and 0 of this because there's no dissociation initially. Then from there, it's going to dissociate. So remember, we use our X value to figure out how much dissociate. So minus X, because we automatically know according to Q, it's got to shift towards products because we can't have a 0. So plus X and plus X. And the nice thing with acids and bases is it's always a 1-to-1 ratio when we're doing these problems. So it's always going to be 1X. Makes our life a little bit easier in terms of calculations. So we end up with 1.0 minus X at equilibrium. We end up with X, and we end up with X. And we're just looking for pH. So what we're really looking for is what is the value of X. So we plug it into our equilibrium expression, which is Ka, or 7.2 times 10 to the negative 4th. Equals the concentration of hydronium times the concentration of fluoride over the concentration of HF. So what does this look like? This looks like Ka, 7.2 times 10 to the negative 4th equals X times X over 1.20 minus X. And yes, if you're looking at this, remember that when K, regardless of whether it's Ka, Kb, Ksp, or anything else K-wise, when K is very, very small, we can make the assumption that this X is small enough that it is negligible for calculation purposes, that we can get rid of it. And that makes our math a little bit easier here to be able to solve this out. Okay, so from there, what do we end up with? Take a second, you calculate it out. You figure out what X is. Okay, so mathematically, we're going to multiply by 1.2. That's going to give us X squared. Take the square root of that. I'm getting my X value to be 2.9 times 10 to the negative second molar. Okay? Well, we can do a couple things with this, but in reality, what do we care about? We care about this value right here, which is equal to x. So now, all we have to do is calculate pH. Well, remember, pH is equal to the negative log of the concentration of the hydronium ion, which is what we just calculated. So pH is going to equal negative log of 2.9 times 10 to the negative second. So we're expecting our pH to be just below 1 here. So take a second, calculate it, see what you get. And I'm getting a pH for this particular solution to be 1.53. No units for pH. So, okay, not too bad. Let's try another one. What is the pH of a 1.5 molar ammonia solution given Kb is 1.8 times 10 to the negative fifth? So first off, recognize that this is Kb. What does that mean? It means we're dealing with, first off, a weak substance. Second off, that weak substance is acting like a base. And ammonia always acts like a base. So we have NH3, which is aqueous. And we can go back through and write our states of matter. Sorry about that. Aqueous. Plus H2O. And because it's acting like a base, what is he going to do? He's going to steal a hydrogen, forming NH4 plus, which is aqueous, and hydroxide, which is also aqueous. Okay. From there, we're trying to find pH. So we don't actually have a hydronium ion in here, but what we do have is a hydroxide ion. So what we're going to do is calculate the concentration of hydroxide, calculate POH, and then from there calculate pH. So let's work through that process. But it's going to work very similarly to what we just did. So we have our I, there we go, C, E, initial change, equilibrium. 1.50 is our concentration for ammonia, 0 for ammonium, 0 for hydroxide. So our shift is going to be towards our product. So minus X, plus X, plus X. 1.50 minus X, X, and X. We set up our Kb expression. 1.8 times 10 to the negative fifth is going to equal products, X, times X, over reactants, 1.50, because we can assume what X is negligible compared to the size of the concentration of the original base, because Kb is so small, so there's a very, very small shift towards products. From there, we just calculate this out. So let's see what we get. You take a second, calculate it, see what you get. Okay, and to mathematically solve, we're going to multiply by 1.50. We're then going to take the square root. I'm getting my X value to be 5 looks like probably 3 sig figs based off original concentration, which is probably what the other one should have been too, but that's okay. I'm getting 5.20 times 10 to the negative third molar. And that is my concentration of both the ammonium ion and the hydroxide ion. I could technically go plug that in and figure out what my ammonia solution is, or what the concentration of my ammonia solution is at equilibrium. But again, I don't care about any of that because all I care about is pH. So for right now, all I care about is POH. And again, how do we know we're calculating POH versus pH? pH equals the negative log of the hydronium ion concentration versus POH equals the negative log of the hydroxide ion concentration. So because we have hydroxide, we're going to be calculating hydroxide. So when we take the negative log of this value, POH equals the negative log of 5.20 times 10 to the negative third. Again, I'm expecting it to be a little bit below 3, so around 2-ish, or between 2 and 3, I should say. I get a POH value to be 2.28, and if we're going to be persnickety about sig figs, it should be 2.284. Remember, after the decimals where our sig figs start in pH and POH. Subtract that from 14, and we get a pH value of 11.716. Okay, so not too bad. Pretty easy in reality. It's no different than what we've been doing. We've just got this extra step of calculating pH or POH as necessary. Okay, I'm going to do one more thing in this video, and then we're going to work through some more problems in the next one. The next thing that we have to be able to do is recognize percent dissociation. This is a common thing that you can see through College Board problems and in college type problems and just general chemistry problems, where instead of them asking for pH or even asking for the equilibrium, they're going to give you a percent dissociation of the original weak acid or weak base, or they may ask you for percent dissociation. So like any percentage, a percentage is a part out of a whole. In this case, percent dissociation is the amount dissociated, meaning how much actually separates, versus the initial concentration of the species. So if we kind of go through and look at this, a 1 molar solution of HF is going to produce 2.7 times 10 to the negative second molar of hydronium or fluoride ions. In technicality, we just have to look at one to figure out how much of it actually dissociates, because it is a 1-to-1 ratio, thankfully. So percent dissociation is our part, how much dissociates, over our whole original concentration times 100. So you could get something that just says the percent dissociation is 2.7, calculate your pH from there, or calculate your Ka value. And there's 100,000 different ways that question could be asked in reality, but I want to make sure we understand what this term actually is looking at. Keep in mind, to increase the percent dissociation, this is going to be kind of interesting. Adding water to this is actually going to allow more of it to dissociate, because if we think about it, our equation, HF plus H2O, water won't affect it because water is a liquid, but what is water going to do? Water is going to decrease the concentration of these species, causing a shift in that direction to get them back to being where they're supposed to be, so that Ka or Kb, depending on what it is, can be fixed. So percent dissociation will increase by adding water, distilled water specifically, to a solution. So just a little bit of tidbit information there. Okay, so let's kind of see how this works. And let's actually plan on doing this on the next video. So you take a second, you read through it, you solve it, and then let's do the answers together in the next video. Thanks, guys.